Morning, everyone. My name is Shikhar. I work for Etsy. And I'll be talking about search time parallelism, essentially trying to get better performance of search by using more of your CPU cores. So the vision is that you can just flip a switch in your config and get 2 to 3 times better performance. Let me tell you a bit about Etsy. It's a handmade and vintage marketplace where you can find things like dog beds or personalized jewelry. There are over 26 million listings on Etsy. By listings, I mean the things that our sellers have listed on the marketplace. And these listings are from over 1 billion shops. I'm on the search infrastructure team. Etsy engineering is very much about continuous deployment. And the way we do it on the search team is we have these parallel sides to our clusters. Only one of them is live at a time. So we deploy code to the side that is not live. We can even reindex there if we need to test our changes. And once we're happy, set it live. And then we can deploy to the other side. So this gives us a lot of flexibility. We have a bunch of different clusters and indexes. Mostly it's Solr master slave. We also have some Elasticsearch. Our most significant index is probably listings. Well, it is listings. It's what gets used when you go to Etsy.com and search for an item or you're just browsing. Until last year, this used to not be sharded. So it was just one JVM with a large heap, of course replicated. And this year we tried something novel to improve performance. So we split it into 8 smaller pieces, the index, and interestingly, they're all running on the same local host. So you can see that we didn't really consider it big enough to distribute across multiple machines. But we were trying to get the benefit from searching these shards in parallel. And we did see a big improvement of the latency tail. That is to say, the 95th percentile latency and the 99th percentile latency improved by a lot. So talking of performance, how do you speed up search? Well, you can certainly make low-level improvements of the kinds that are happening with Lucene and Solr all the time. And they help a lot because after a point, you have your index in RAM. Search is CPU bound. So that helps. And on the other hand, you can parallelize, actually use more of your CPU cores within a search request. That's a screenshot from HTOP on one of our newer Ivy Bridge servers. So it's got 20 physical and 40 virtual cores. At Etsy, we like to run on bare metal. But this kind of configuration is also achievable in the cloud and makes a lot of sense for search applications. So this presents a tremendous opportunity to parallelize and get better performance. And any discussion of parallelism isn't really complete without the Amdahl's law, which is giving you the limits on the speed up that you can get. It's going to be limited by the sequential amount of work that you need to do. So it's intuitive, but good to know what the bounds are. Just to have a quick overview of sharding. This is very easy to do with Solr Cloud and Elasticsearch. And if you want more control, you can hand roll it with Solr distributed search, or even at a lower level with Lucene. Typically, you would be hashing the primary key for your documents and distributing it over the number of shards you have. So the hashing tends to give you a reasonably good distribution, which is important because you want your shards to be about the same size and for them to have reasonably similar index statistics. So if you can parallelize in this manner by sharding, why would you not want to shard? Sounds great. Well, once you go distributed, there's certainly a lot more challenges to deal with. And most importantly, you have all these additional moving parts, and as a consequence, lots more failure modes. For example, if one shard has a garbage collection, or it's warming up an index searcher, it could impact your overall latency. And a lot of things are easier to do in process, so distributed search can't really keep up ever. And additionally, your index statistics, it's very hard to ensure that they'll be the same across all your shards, which may or may not matter in your use case. So because of these drawbacks, it can be tempting if you need to shard, your index fits in RAM easily, to just defer it. So the alternative that I'll be focusing on is parallelizing at the segment level. The Lucene index already consists of these append-only write-once segments. They tend to be structured as the older segments being fewer in number and larger in size. And as you index new documents and commit, new segments get created, and in the background, the merge policy is merging them together. So the idea would be to treat these segments, which are like essentially mini indexes, as shards, and search them in parallel. So before we go into that in more detail, let me give you a quick lowdown on collectors. So this is just a Lucene abstraction for accumulating results. They have this collect method that's being called for every hit with the doc ID. And they have the scorer available, so if they need the score, they can get that. And once you're done with the collection process, you can get the results out of it. Like depending on the collector, it could be the top n hits, your group results. And to be clear, this segment-level parallelism is not a new idea. It's an existing solution in the form of this alternate constructor for index searcher. Which takes an executor service argument. Unfortunately, this does not work in the general case, where you need to search with an arbitrary collector. It's special case for the top doc collectors where you want top n hits based on some sort criteria. And the reason that it can't work in the general case is that it's hard to scale this special casing. It's not composable to be. This pattern of special casing is not composable. You can't special case for every possible permutation of collectors you might have. In our case with Solar, we use a timeout on the search. So we have a time-limiting collector that's wrapping. Solar likes to use this multi-collector, which has the actual top docs collector, and Solar's docset collector. So this can't currently be parallelized. And in search of a general solution, if you look in the index searcher source code for the search method, you see this comment. Maybe we should just synchronize the methods on a collector. So we can, instead of searching the segments in sequence, we can search them in parallel safely in a thread-safe manner. However, you can imagine that collect is being called for every single hit in your query. So there's going to be massive contention. So it doesn't seem like a great approach. So the proposed solution that we looked into is this refactoring of the collector API so we can parallelize search. That's what we played around with. Let's have a review of what the API looks like right now. So in the Lucene 5 branch, it's a simple collector interface that gives you can get the leaf collector out of it at the segment level. And that's what actually acts as the accumulator. It has the collect method being called for every hit. Actually, in branch 4x, this is all on the same interface. This was partly inspired by this refactoring because we needed a way to cleanly separate out the segment level state. So we want to add some new methods on collector, 3 new methods. Is parallelizable, whether it's safe to parallelize the search. Set parallelized, you want to let the collector know that you intend to parallelize. And done is just a callback that gets invoked when you're done with the search, so it can do any kind of consolidation internally. And on the leaf collector, we just have one new callback method, leaf done, for when you're done with the segment search. To describe these in a bit more detail, the idea behind is parallelizable is that since we need every collector in the path for a search to be parallelizable, we need a way to know which ones are and aren't. We can't just assume it. And the nice thing here is that we have a way to start attacking the collectors one by one. By default, they can just return false. So as you can see, for multi-collector, it's looking at all the collectors that might be wrapping, and unless all of them are parallelizable, it's going to return false. With set parallelized, the idea is to not penalize serial search. Now, sometimes you can, or most of the time, you might be able to make the serial and the parallel search implementation about the same. But occasionally, the trade-offs, with the trade-offs, it might be worth using a different approach, because you might need a lot more additional state or a lot more computation. And we'll see an example of that. Now, the core idea here is that we don't want to use synchronization within the collector implementations. We want to use non-blocking constructs. And the way to get that is to have some guarantees. And these guarantees are that you have mutual exclusion for these methods in the form of the guarantee that these methods will always be called from the primary search thread, which is to say the caller for the search method. So they become safe places to act on any shared mutable state you might need. And to support all of this, the search method in index search needed to change. So it's been factored out into the search strategy interface, just a way to get it to be pluggable. So by default, you have the serial search strategy. And when you want parallelism, you can use the parallel search strategy. That takes the executor, which can be a thread pool, for example. And this parallelism argument is interesting. So it's throttling how many tasks will be concurrently running at the level of the search request. You might have a thread pool of 128 threads, but if you set this to 4, at the level of the individual search request, you're only going to have 4 segments being searched at a time. And I want to clarify that we're not just trying to parallelize collection, which might seem like it's not always that expensive, but search as a whole. And we need collectors to be parallelizable for that. So any kind of I/O that's happening in the query, there's scoring happening, this stuff is already thread safe and at the segment level. Collection also you might think is at the segment level, so might be safe, but actually, for the most part, these are operating on shared state between the leaves. So we need to get parallelizability into the API to be able to do this safely. So let's have some concrete examples. This is the total hit count collector, which is doing something pretty simple. It's giving you a count of the number of hits that matched your query. In the serial case, you can imagine it's very simple. It's just an integer counter, and when collect gets called, it gets incremented. In the parallel case, we introduce at the leaf collector level an additional counter. And when you're done with the leaf, this gets merged in. So this was really easy to parallelize, and there are actually a bunch more like this in the Lucene Solar code base, where it's almost criminal to not parallelize. Then we have the Solar docset collector. This is a really interesting exercise. So this thing is creating a bit set of all the hits that match the query, which turns out to be very useful for things like faceting or filtering. Now, internally, this bit set is represented as a long array. So every long is representing 64 documents that might have matched. Now, the catch is that these doc IDs inside this bit set are at the index level. So to explain what that means, if you look at the table, each row represents the range for each segment. Now, internally within these segments, the range starts relatively at 0, and they have an offset doc base, which you add to it to get the index level doc ID. So they have independent ranges, but if you think of it in terms of the bit set, you could have race conditions on the boundaries where the same long elements might be concurrently updated if you're doing it in parallel. So the trick we can use here is that we know what the boundaries are. The first 64 and the last 64 documents in the segment, we know what those will be, and those we can just collect into some longs at the segment level. And then when we are done with the segment, we can merge those in. And for everything else, we can collect directly into the shared bit set. So we can parallelize this quite cheaply without adding a bunch of additional state. Like, we don't need to go all the way to having segment-level bit sets and then merging all of those. In fact, Lucene has this facet collector, which is entirely just segment-level bit sets. So we don't even need to do these gymnastics there. It's already very parallelizable. So far we saw total hit count collector and the doc set collector, where we just need a few more additional fields, and merging is quite simple. With the top doc collectors, it's a bit more, trade-offs are a bit, need more consideration. So the way this is implemented is that it's got a bounded priority queue, sized at the number of hits you want to get out of it. So if you want the top n hits, it's going to have n elements inside this bounded priority queue. And it's currently implemented by, for parallelization by having additional priority queues using a lazy pool, which is to say that when you create a new leaf collector, it grabs it from this pool. If a queue isn't available, it'll get created. And when you're done with a leaf, it gets returned to the pool. And finally, when you're done with the search itself, these auxiliary queues get merged in to the primary one. So this gives you safety for parallelizing. And this is actually where the parallelism factor in the parallel search strategy comes in useful. It gives you an upper bound on the number of additional priority queues you will have. So if you set your parallelism to 4, you're only going to need 4 additional priority queues. So in terms of trade-offs, yes, you're using a lot more memory, certainly. And there's more computation because you have to merge these queues in the end. So now to the numbers. This might look like a wall of text to you if you aren't familiar with this benchmark. It's a standard Lucene benchmark called Lucene util, which builds a Wikipedia index and runs a bunch of queries for a bunch of different kinds of queries in a number of iterations. In the serial case right now, where you're comparing the current trunk with the serial search strategy, with this patch, there appears to be a small penalty. Some of the time it's faster, actually, but on average it appears to be maybe 10% slower. I'm not sure if this penalty is real. Now, when you actually use the parallel search strategy, that's when you start to see really big wins. For most queries, it's 2 to 3 times faster. It's terrific. So that was benchmarks. We actually tried it out for real. Well, somewhat real. This is in the lab. We have these experimental clusters that we can deploy branches to. So we deployed the patched Solar Lucene, and the Solar index searcher was hacked so that you could use a parallel search strategy. And we also have tooling around pumping requests at hosts. So we're always capturing our requests in logs, and we can replay those for load testing and even comparing results. So when we ran that, we saw that the serial search strategy the parallel search strategy gave some very big wins. You can see that the 99th percentile latency is pretty much halved, and the 95th percentile latency was easily better by a few hundred milliseconds. The median also looked really good, although it's not shown here. Now, as you can expect, this had an effect on throughput. So we're certainly doing more work overall, although we're getting better latency because we are parallelizing. As you can expect, there's some concurrency overhead, just using all the concurrency primitives in the JVM. We have context switches because you're using more threads that are active at a time. And there is merge cost to any segment level state that you need to merge in to get the global result. But also you might be making some locally optimal choices. Like with the top docs collector, you only know about your current priority queue rather than in the serial case, you have one priority queue. So you know what the globally optimal choice or the globally optimal decision is, whether or not a hit should make it into the queue. Starting to wrap things up, I'd like to have a comparison with sharding. So this approach is limited to a single JVM, whereas with sharding, you can scale across JVMs. You need to use distributed search with sharding, though, because even if you were to somehow, you can run the shards in the same JVM, it's structured such that you need to use distributed search. Whereas with this, you don't need distributed search, so all your normal features are going to work. On the one hand, this is sensitive to segment count and sizing. And by that, I don't mean that you have some smaller segments and some bigger ones. That's OK, because those tasks are just going to finish faster, and then the next one will start faster. So that's fine. But say if you were to optimize or force merge your index down to one segment, suddenly you don't have parallelism. So the merge policy becomes more significant here, where you don't tend to have that much control. Like with sharding, you can control the shard sizes. But at the same time, it should be noted that with sharding, you're prone to shard lag, where variations in shard response times can impact your overall latency. There's a lot more serialization overhead to using sharding, whereas this is all happening in the same process. There's no serialization, so there's less overhead. And certainly, this is still just a patch. It needs review, more testing. While sharding, you can pretty much use already. You can use this too if you're bold. Something my colleagues have been pointing out, why can't we do both? Why not have sharding and segment-level parallelism? On the one hand, you're already sharded. You could shard more finely. But that brings more of those problems. They become more significant. You're more prone to the failure modes. You have more JVMs to deal with. So it could be an interesting direction to explore. In terms of next steps, I'd like to figure out whether that serial penalty is real. In theory, it should be possible to eliminate it, because we have this way of telling the collectors whether or not they're running in serial or parallel mode. There are some semantics around exceptions during collection that were pointed out in a JIRA that need to be figured out. And a lot more collectors can be parallelized. We just really cared about the ones to get numbers out, like that were in the hot path for a search, like top score doc collector, doc set collector, all these wrappers like multi-collector and time-limiting collector. But there are tons of collectors in Solar Lucene that are just returning false for is parallelizable. And your contributions are very welcome. That's the JIRA again, Lucene 5299. Thanks a lot for being here and listening to me talk. I hope you found it interesting. I'd like to mention that we're hiring on both the search infrastructure and search product teams. There's a bunch of us here, all these guys here, so you should come find us. I think we have 5 minutes for questions. Go ahead. Sir.
You said that performance of parallel search is very dependent on the number of segments. So what typical number of segments which you measure?
I wouldn't say it's dependent on the number of segments unless your parallelism factor is more than the number of segments you have. So if you have more segments than that, that's fine. So even if some of the segments are smaller, the search for that segment will finish faster, and then it can take over for the next segment. But if you want to use 8 threads at the search request level, but you have 4 segments, you can't get better parallelism than that.
Basically, what you're saying, the number of segments, the segments have to be roughly of the same size, and they have to be more segments than 4, right?
More segments than your parallelism factor, but they don't necessarily have to be the same size. I wouldn't say that. But yeah, it's true that it's going to be at least as slow as the biggest segment.
What about testing? Have you considered vectorization of testing as well?
No, we didn't look into that yet. Go ahead.
So the index searcher in Lucidworks takes an executor service, and it seems to collect per segment. I didn't look at the details, but I noticed it recently. So what's going on there versus here?
So that approach is limited. Yeah, that's the existing solution for having segment-level parallelism. And that's got special cases for top score doc collector and the top field collector. But as soon as you start to have wrappers around collectors, or you don't want the top docs, but you're doing faceting or grouping, that's not going to fly.
Basically, it works for certain searches,
Yeah.
but not for most searches that are more common these days. Okay.
Yeah. If you're using Solr, it's not workable at all. If you're using Lucene directly, you might be able to use it. Go ahead.
So earlier, you had mentioned that it's limited by the biggest segment. So if you optimize on a regular basis, is there much to be gained from this approach?
I guess not in that case, yeah. If you're optimizing down to one segment, maybe like once a day or something. But I understand that when you optimize, you can even say the number of segments you want at the end. So yeah, that might be an option. In that case, yeah, you could get benefits from this. I haven't tried out how well it works with it.
Yep, that's right. To your question about whether you're actually slowing it down in the serial case, did you run your experiment sort of using the standard without your patch? Because at least that would be you've got the setup. That would be a real-world example, which might help answer that question.
Are you talking about the replay testing? Are you talking about the replay test?
In your experiments, you have 95th, 99th percentiles. So did you ran this with and without, with your patch, with and without parallelism?
That's a great question.
Without your patch.
Yeah.
Without your patch would be interesting. If
Yeah.
you're saying in your case that it might not be, it might be the same in the benchmark. This is at least real-world examples.
Yeah, that's true. Yeah, this is with the patch using the serial case and with the patch using the parallel case.
It'd be interesting to see without the patch.
That's true.
I have a question. So with your setup and your tests, I was just wondering what kind of disks were you using? Because the fact is, if you're giving it overwhelmed the disk with too much I/O requests, it might not necessarily provide you with so much benefits. On the other hand, SSDs might perform quite well for things like this.
Yeah, we like to have our index entirely in the OS file cache. We have tons of RAM on our machines, and yeah, we're using SSDs.
Okay.
Okay, great. We're out of time. Thanks a lot again. Right.